Hello and welcome. In this video, we will explore the fundamental concepts of the PN junction diode. We'll break down everything you see in this diagram, starting from the very basics, to build a solid understanding of how these essential electronic components work. Let's begin at the top with the title, PN junction diode. First, let's look at the standard symbol for a diode. It consists of a triangle pointing towards a vertical line. The terminal connected to the flat base of the triangle is called the anode, which is represented by the letter A. The terminal connected to the vertical line is called the cathode, represented by the letter K. This symbol also helps us understand the direction of current flow. The arrow in the diagram, colored in cyan and labeled with a capital I, shows the direction of conventional current. Conventional current is defined as the direction that positive charge would flow. As you can see, it flows from the anode to the cathode, in the same direction that the triangle symbol points. Below that, we see another arrow, colored in yellow, pointing in the opposite direction. This arrow represents the direction of electron flow, indicated by the symbol E with a minus sign. Electrons are negatively charged particles, so they flow in the opposite direction of conventional current. They move from the cathode, which is the negative side, towards the anode, which is the positive side. So, to summarize, conventional current flows from anode to cathode, while electrons flow from cathode to anode. Now, let's look at the diagrams just below this. On the left, we see the diode symbol again, clearly labeling the anode, or P side, and the cathode, or N side. The terminals are marked A for anode and K for cathode. To the right of the symbol, we see a block diagram which represents the physical structure of the diode. It's a rectangle divided into two sections. The left section is labeled P, and the right section is labeled N. The terminal connected to the P section is the anode, labeled A. The terminal connected to the N section is the cathode, labeled K. This shows that a diode is fundamentally made by joining a P-type semiconductor material with an N-type semiconductor material. Let's dive deeper into this structure with the larger diagram in the center. This diagram shows a close-up of the PN junction. The entire block is divided into two regions. The left region is the P-type material, and the right region is the N-type material. The line where these two materials meet in the middle is called the junction. Inside these regions, we see small circles and dots representing charge carriers. The key indicates that the hollow blue circles represent positive charges, which we call holes. The solid yellow dots represent negative charges, which are the electrons. Let's examine the P-type region on the left. As you can see, there are many hollow blue circles and only a few solid yellow dots. This illustrates a key property of P-type material: the holes are the majority charge carriers, meaning they are the most abundant. The electrons are the minority charge carriers, meaning there are very few of them. Now, let's look at the N-type region on the right. Here, the situation is reversed. There are many solid yellow dots and only a few hollow blue circles. This means that in N-type material, the electrons are the majority charge carriers, and the holes are the minority charge carriers. So, how are these P-type and N-type materials created? The arrows pointing down from the PN junction diagram explain this process. Both P-type and N-type materials are what we call extrinsic semiconductors. This means they are not pure, they have had impurities intentionally added to them. This process of adding impurities is called doping. To create the P-type material, we start with an intrinsic, or pure, semiconductor like silicon, abbreviated as Si, or germanium, abbreviated as Ge. This pure material is then doped with a trivalent impurity. Trivalent means the impurity atoms have 3 electrons in their outer shell. Because they have one less electron than the surrounding silicon or germanium atoms, they create a hole, or a space where an electron could be. This is why it's also called an acceptor impurity: it's ready to accept an electron. To create the N-type material, we again start with a pure semiconductor like silicon or germanium. This time, it is doped with a pentavalent impurity. Pentavalent means the impurity atoms have 5 electrons in their outer shell. This provides an extra, free electron that is not needed for bonding with the surrounding atoms. This is why it's called a donor impurity: it donates a free electron to the material. The text below this section summarizes the overall process. we are adding impurities into an intrinsic semiconductor to create these extrinsic p-type and n-type materials. The diagram also defines an important state of the diode. In yellow text, it says, unbiased diode, when no external source is connected to the diode. This means that everything we have discussed so far describes the diode in its natural state, with no battery or voltage applied to it. Finally, let's look at the flowchart at the bottom of the image, which provides a wonderful summary of semiconductor types. At the very top, we have the general category, semiconductor. This branches into two main types, intrinsic semiconductor and extrinsic semiconductor. An intrinsic semiconductor is described as the pure form of materials like germanium, Ge, or silicon, Si. It has no impurities added. An extrinsic semiconductor is an intrinsic semiconductor that has been doped. This category further branches into two types, p-type and n-type. P-type semiconductors are created by adding a trivalent impurity, which is also known as an acceptor impurity. The diagram lists some common examples of trivalent impurities: aluminum, boron, gallium, and indium. N-type semiconductors are created by adding a pentavalent impurity, also known as a donor impurity. Common examples of pentavalent impurities listed here are antimony, arsenic, bismuth, and phosphorus. So, to recap, a p-n junction diode is created by joining a p-type semiconductor, which is rich in positive holes, with an n-type semiconductor, which is rich in free electrons. This simple but powerful structure is the foundation for many electronic devices. The symbol for the diode, a triangle pointing to a line, shows the direction of conventional current from the anode, P side, to the cathode, N side.